Hi, my name is Robert Kerdman, and this is my Lab 2 on black hole motion. So to begin, I'm going to just lay out the presentation. I'm going to cover the introduction, our models, both the experiments, the discussion, and the conclusion. So to begin the introduction, I'm going to talk about the purpose. The purpose of the lab is to calculate the mass of a black hole given a known mass for an orbiting star. This can be done with the principles of gravitation with FNet parallel and perpendicular components. And the second purpose was to find a stable orbit for a spaceship around a planet and moon by adjusting initial velocity, demonstrating the influence of a multi-body system. The preview of the results are below. The mass of the black hole, 1.107 times 10 to the 44, and the initial velocity of the spaceship, which was negative 1,044,000. So here are the fundamental principles. Sorry for the handwriting. So first, we know with Newton's second law, that Fnet equals Fnet perpendicular plus Fnet parallel. Using the velocity update formula, we can find VF using V initial, and we can also use the position update formula to find the final placement using the average velocity, and also the gravitational force, which is the force used in the the velocity update formula, is here, which is negative gmm over r squared. So for part 1, we define the system as the star and the black hole and the surroundings as everything else. And for the initial conditions, the mass of the star was 2 times 10 to the 30 kilograms. Time was 0, the initial time was 0, and delta t was 0.0001. And down below is our formula for the initial velocity. And then for part 2, the system was the spaceship, the moon, and the planet, and the surroundings were everything else. And below are the initial conditions for everything else, the masses of all three, the initial velocities of everything, and the time we started at 0. So here's our code. As you can see, we use a while loop to update the velocity and position, and then calculate the using the force that we have. We then calculate the position of the star, or the position of the star at the very end, and the mass of the black hole. To the right, these are the graphs with the arrows and the vectors and everything, and our final print statements. So as you can see on the right, we calculated Fnet parallel, Fnet perpendicular, and using those values, we found the mass of the black hole. Now, this is for part 2. As you can see, we used position update formulas and velocity update formulas to find the forces, which we use to balance out and find a stable position and stable initial velocity for the spacecraft. For our results, we found the stable orbit, which was non-figure 8 shaped. We did a lot of trial and error with the initial velocity, but this is the stable orbit that we found, and it's lasted for over 700 hours. So for the possible sources of error, we did use a finite time step for part 1, which would give us a lot of room for the function not to be smooth, which kind of gives like a level of error. Rounding could be an error, and simplification could be an error for that as well. And for part 2, it was hard to find the initial velocity due to guess and check, and we had to assume there were no outside forces. So what does this mean? This is asking to discuss how the net force and its components are different from the rate of change of momentum and its components. So mathematically they're the same, but for net force, you need to know every external factor exerting a force on the system. However, for the rate of change of momentum, you only need to know the system's change in velocity. For part 2, if you want to predict the motion of the entire system, what would you need to include in your computational model? And you need to consider all forces within the system and all aspects of the surroundings that are acting on the system in any way to correctly model the motion of the entire system. Thank you very much.